So thank you for coming for the second talk of today. It's a pleasure to have Jason with us. He is assistant professor at OFI in Princeton. He works on many interesting works. We have a few Princeton people today, which is good. And without further ado.
Thank you. Thank you very much, Morgan, for the invitation and for also organizing this wonderful workshop. It's great to be here. Okay, so today what I'd like to do is to talk about some brand new work of mine. So this is joint work with a postdoc, Omar, and then a PhD student from ECE, Electrical and Computer Engineering at Princeton. Okay, so I want to start off by just giving a motivating example that's going to set the stage for what I'm going to be doing throughout the talk. So let's suppose that we have a problem where we want to predict patient outcomes from some routine measurements. So at test time, the patient comes in and we only observe basic vitals, so things like maybe blood pressure or heart rate. But then maybe during training, we have other instances of very expensive lab tests that are more comprehensive, so things like full blood panel, like lipids, sugars, that sort of thing, or even genetic markers maybe. And we might have a lot of this data, okay, but this data might not be available at test time, only during training. And among this data, we could have two different types. So maybe we have few patients that are actually labeled. So in other words, we do observe their vitals in their labs, plus some outcome variable of interest. And then we also might have many, many patients where we don't actually have an outcome. So we still have this more comprehensive maybe set of data, but maybe we don't have an outcome. And so the challenge is, well, can we use this rich unlabeled data to build a better predictive model that only needs basic vitals? So this is kind of a motivating example for what I want to do. Okay, so we start off with a training data set. It's pretty small. We have some side information, which throughout the talk I'm going to call W. And this is only available during training. So at test time, I'm not able to use the side information. I only have X. And in that case, my target is just going to be the conditional expectation of Y given X. So again, I can only use this W information during training, but at test time, I have the X's. And so my target then is this conditional expectation. Okay, so just to be more precise, so what I observe here is I have n labeled samples. So I observe my X's. So this is what I have at test time. And then I have my W's, that's my side information. And then I have my labeled information. And I have little n. And this paradigm was introduced about 15 years ago by Vapnik, which he called learning using privileged information. So the W's in that line of work would be called privileged information. I'm calling them side information, but that's what he used. I'm also using W's. If you're familiar with this line of literature, they use X stars, but stars for me means something else, so I'm going to avoid that. And then more recently, there was some really cool, very interesting work by Eric Shia and Martin Wainwright at MIT, where they said, okay, well, what if we don't just have these n labeled samples with the covariates, but we also observe unlabeled samples that are paired. So we have the X's and then we also have the W's. And so the question then is, how do we combine all this data together to improve prediction for Y given X? Okay, and so throughout the talk, I'm going to concatenate the X and the W data together, and I'm just going to call that vector Z. Okay, so Z throughout denotes this combined vector. So again, we have n labeled samples with our side information W, and then we have m unlabeled samples with the paired data that have the X's and the side information, but no labels. Okay, and we want to combine things. So the main question is, can we use the side information to improve the performance beyond just ignoring that side information and training only with the X data? So that's going to be the main question. And we're going to kind of see, when is this possible and when is this not possible, and hopefully be able to characterize when that's the case. Okay, so I want to go over this paper that I mentioned by Eric and Martin. And so their approach, they called it prediction aided by surrogate training. So they used yet another set of terminology. So they called these W's surrogate variables. Okay, so there's privileged information, surrogate variables. I'm calling it side information. They're really all one and the same thing. So what they did is they say, okay, well, let's first start off by learning from these rich features. So the rich features are going to be these X's and the W's. And so what they first do is they build a model on these Z's. And so they fit a model using the labeled data. Okay, so now on this, remember I had n samples, and on those n samples I have the labeled data. So what they do is they train a G hat. So this is what I'm calling the rich model, the rich view model, because it uses both the X's and the side information. Okay, and then what they do is they transfer knowledge to the deployment model. So this is the model that you would actually be using for predicting Y given X via this pseudo-labeling mechanism. So what they do is they take this G hat that's learned at the first stage, and they just plug in the unlabeled samples. So these are the rich view samples, right? But they're unlabeled, so they don't have corresponding Ys, to create these pseudo-labels, which I'm going to call Y hat. Okay, and so I have M of these because I have M unlabeled samples. So I'm evaluating at all of the ZJs for the unlabeled data. Okay, and then what they do is they then train a deployment model on the labeled and the pseudo-labeled data. So they basically just treat the pseudo-labels as basically being true labels, and then just train a model. So now we're minimizing the sum of these squared errors, where I'm minimizing over some function class. And yeah, for me, G and F are kind of more generic function classes. I want to keep them generic on purpose. You could think of them as just being nice, maybe convex sets for now. Okay, so this is what they did, and I want to talk about some issues with this, with a data example. But I first want to tell you about what we propose, which is a variant of this, but it's a little bit more general. So what we're going to do is we're going to do the following. So let's suppose that someone gives us some pseudo labels. Okay, so some Y hats. And then what I'm going to do is I'm going to train the deployment model. So the deployment model, again, is the model that I'm using for predicting Y given X. So it's just I'm just treating the Y hats now as labels, and then fitting a model to this. So that's going to be my F hat. Okay, but now I'm going to give myself the opportunity to recalibrate these pseudo labels. And so I want the pseudo labels to be close to the model F hat, to the deployment model, but I also want them to be true to the real labels as well. I want them to kind of mimic the true labels, right? So this squared error here is on the unlabeled data, and then this constraint here is on the labeled data. Okay, and so this constraint here ensures that my pseudo labels then are going to be, roughly speaking, true to the actual labels that I have to work with. And this new parameter here kind of modulates, you know, the degree to which I'm being true to these true labels. Okay, and then I'm just going to go back and forth, right? So iterate this in a loop until I get convergence, right? So first, so I update the deployment model with some pseudo labels, recalibrate the pseudo labels, go back the deployment model, and so on and so forth. Just iterate back and forth. Okay, and so it turns out that under some convexity conditions, which is basically just that the function classes are convex, this alternating algorithm will actually converge to this kind of joint optimization problem, where now I'm jointly optimizing this objective over F and G simultaneously, subject to this kind of calibration constraint. Okay, and so this new constraint here is going to bounce between focusing on the deployment model kind of versus the rich view model that uses the features that contain W, my side information. Okay, so just a few more comments about what this new parameter is. So if the function classes are nested in this way, so if F is a subset of G, then my parameter new should satisfy this inequality. So these are kind of this is like the feasible set for which new belongs. So at the lower end, I have the smallest that I can get if I'm predicting Y with the rich view models over the function class. And then on the upper end, I have the smallest that I can make the error if I'm predicting Y with just the features X alone. Okay? And so if I'm above this range, so if new is equal to this or above it, then actually the unlabeled data is just completely ignored. If I'm below this range or at the lower end here, this actually just reduces to the first algorithm I presented by Shia and Wainwright, by Eric and Martin, which is the prediction aided by surrogate training. And I'll show you a few examples that show that you really actually kind of, in most cases, want to be somewhere in between these two extremes. Okay, so let's see an example of that. So let's just fit a linear Gaussian model. So here I'm assuming that my Y's are some linear combination of the X's and then also the W's, the side information. And so if I have some dependence between X and W, well, okay, I have a Gaussian model, so my target, the conditional expectation, it's also going to be linear, and I have this parameter vector then that the deployment model would be trying to estimate. So in this setup here, I have 50 labeled samples, I have 100 unlabeled samples, the dimension of X is 10, the dimension of W is 20, and the signal that I have for the side information variable, for the W information, is in this case quite large. So I've chosen it to be pretty large. And what's being plotted here is, so the y-axis is the test MSE, and then on the x-axis is this constraint value. So this is the calibration constraint value for those pseudo-labels. Okay, and then the red bar up here is what I would get. This is kind of the baseline that I would get if I only use the x information. So this is kind of the baseline that we're comparing things to. And as I said, right, if nu is very large, right, basically at the upper end of things, then it's almost as if I'm completely ignoring the unlabeled data. And in that case, it's not surprising why these plots show that I'm kind of converging to the X-only case. This is a case where actually it is true that you would want to take nu to be as small as possible, right? So that the MSE is smallest when I take the smallest feasible constraint. And in that case, that corresponds exactly to that method that Xia and Wainwright proposed. Okay, now that's not always the case. So if my side information, if my W variable isn't that informative, so in other words, if I have a smaller L2 norm, then I see a different type of pattern. So everything else really is kept the same. The only thing I've done is just change this. And so you can see then that actually it's not a good idea to take the constraint to be as small as possible. In fact, actually you can get negative transfer, so you end up doing worse than if you just used the X-only data. And obviously you don't want to be in a situation like that, right? I mean, you want the side information to be at least as good as ignoring it, right? So yeah, so it is important actually to get this constraint right. Okay, so what I want to do then is it's a little bit awkward to work with the constrained form of the optimization problem, or that joint optimization problem where I'm optimizing over F and G simultaneously. So let me consider the Lagrangian form. So here what I'm doing is I'm just adding lambda times the penalty that I have, that calibration constraint here. So this is now the thing that I'm trying to minimize over F and G. And then let's also look at the population version of this. This is just taking expectations, and so this is the quantity that I would be minimizing in the population. Okay, so lambda is playing the role of nu here, and they behave inversely, right? So lambda being small corresponds to nu being large, and vice versa. Yeah, sure. Sure.
If there's no unlabeled data at all, then is there any value to still see?
There is actually. So that's the work of Vapnik et al. So that's the learning using privileged information paradigm. Is you don't have any unlabeled data, and you just want to see, okay, well, if I just have labeled data, but I have these in their language privileged information, then how can I use this to improve things? And the setting that they're usually considering is classification in this line of work.
The methods that you're exploring, if I don't actually have any labeled data, they would just ignore them. For example, this past.
Oh yeah, So the methods I'm describing are more tailored for this setting here, where I also observe the paired data, so the x's and the side information, but no y's, so it's unlabeled. So they are kind of in the constraint, right? Because when I create these pseudo labels, I'm working with the enriched data. So these zi's here are the x's and the w's and the labels. So I am actually using the labeled samples at that level to create the pseudo labels. But the point is that they are using these enriched information. Does that kind of answer your question? Yeah. So the pseudo labeling uses the labeled data, but it specifically uses the enriched data with the side information. Yeah. And then at the stage where I'm doing the pseudo labeling, there I plug into the G that I've learned at the first stage the unlabeled enriched data. So the ZJs that are the XJs and the WJs, but without any label.
If you don't then you're not actually using pseudo labels to do.
Then I'm not using any pseudo labels. Yeah, that's right. That's right. I see what you're saying. Yeah, that's right. That's right. That's right. Yeah, yeah. That's right. Good question. Thank you. Okay, so what I want to do next is I kind of want to describe, well, what do the population minimizers of this objective look like? And so you can show actually that the population minimizers of that objective satisfy this fixed point equation. And you can show under certain cases that this fixed point equation can be solved. So in particular, if my mu belongs to both f and g, and eta here, which is the conditional expectation of y given x and w, so given the site information as well as the features that I'm interested in, that belongs to g, and f and g are convex, then the minimizers have this form. So it turns out that the minimizer for f star, so this is the target for the deployment model, is actually equal to mu, the conditional expectation of y given x. So in that sense, it's well calibrated. And then g star, which is the target for the rich view model, it is some convex combination where the convex combination weights are determined by that regularization parameter as well as the unlabeled and labeled sample sizes. It's some convex combination of the target for the deployment model, the conditional expectation of y given x, as well as the target for the rich view data, which rich view model, which in this case is the conditional expectation of y given x. So it kind of interpolates between the two using this kind of convex combination. Okay, so now what I want to do is I want to talk about, I want to introduce a quantity that's going to determine the quality by which these additional samples, unlabeled samples, and this side information can help the prediction for y given x. Okay, so let's introduce this quantity, which is going to be the correlation between the two model errors. So this is the correlation between the error that I have for my deployment model and then the error that I have for my rich view model, the model that I'm using to form these pseudo labels. Okay, and so the key takeaway actually in all of this work is really that if this is small, so if the errors that these two models make are more or less orthogonal to each other, or at least if this is bounded away from one, then you'll see actually in the risk bounds that the side information really helps. Okay, and the reason for this is because then the side information, the W, captures information about y that x misses, that x does not contain. Conversely, if these errors that these two models make are highly correlated, then you see more limited benefit, and so there's kind of more redundant information that W has in y given x. And I guess it kind of makes sense, but the interesting thing for us at least was that a quantity of this form, which was the correlation, captures this story. Okay, so here's the risk bound. So the risk bound states that again, this is f hat as my deployment model, and so this is the expected integrated squared error. And what it says is that I can first of all upper bound this risk by 1 over gamma. I'll explain what gamma is in a second. Okay, times the expected difference between the population objective at my global minimizers of the empirical risk, and then the true minimizers of the population risk. And using some kind of tricks from empirical process theory, you can further upper bound this difference by this quantity. And it's kind of different maybe from what you're used to seeing. So let me just explain in a nutshell what's going on. But this 1 over gamma here is the quantity that really measures how well this additional side information improves things, and it is a quantity that incorporates this rho star. Okay, so basically what happens is when this rho star is bounded away from 1, so when this rho quantity here, this correlation is not too large. So in other words, when the models make independent errors or errors that aren't too correlated, then you can show actually that this quantity up here scales like 1 over n. Okay, and n is the total number of samples that I have for my unlabeled and labeled samples. So in other words, if this correlation is small, it's almost as if those pseudo labels that I'm generating, I can almost treat them as actual real labels, and then the risk bounds that I'm getting basically are going to scale like 1 over the total number of samples. And you know, I have some quantities here which capture the complexity of the functioning spaces that I'm working with, but they're not too important. For finite dimensional spaces, these are going to scale like the dimension of the model times maybe log of sample size, something like that. Okay, so the important thing is that when rho is bounded away from one, when the two models make errors which aren't too correlated, then you can almost treat this pseudo-labeling mechanism as providing labels which are true in some sense. You've almost like effectively expanded the sample size to being fully labeled. Okay, on the other hand, you can show that if rho equals 1, then actually this rate reduces to the case when I just have my X-only data, so just my labeled data. So it degenerates to the case where I'm just ignoring that side information. Okay, yeah, question, yeah.
So from this, seems that the larger that you choose lambda, the better, right? You have a larger lambda, then you have a larger gamma, and then
There is some balancing that's going on here. It's not always the case that you choose the larger lambda is better. Yeah, because the correlation itself also depends on lambda too. Yeah. So anyway, we have some theory where we analyze a linear model out to the wazoo and we can say very precise things, but it's not terribly illuminating because I really want to develop a more general principle that's at work here that goes beyond just kind of these more specific cases for the linear model. Yeah, but you can kind of analyze all these things very carefully in the linear model setting, and in that case you can show something kind of similar to here. That in a lot of cases, the lambda, which corresponds to this new constraint, kind of lies somewhere in between two extremes, and so it's not always the case that you want to take it to be as large as possible. Yeah. But the main message here is just that if the deployment model and the rich view model make errors which kind of aren't the same, which are decorrelated in some way, then that tells you precisely that this side information, unlabeled side information, is going to help. That's the main story here.
it characterize how depends on mu or lambda.
So again, it's hard in general, but for a linear model case, again, if you make certain assumptions, it's still actually an extremely delicate question. It's not trivial at all, even with the linear model, but yeah, if you go beyond that, if you consider like nonlinear models, then I think it becomes extremely hard. Yeah. So again, it's mainly like if this quantity is controlled, so if this correlation is bounded away from 1, then you have these nice properties. And if you want to determine, okay, well, when actually does that occur? It's, yeah, unfortunately more on a case-by-case basis. And for the linear model, you can do it, but for other linear models, I think it's just really difficult and probably almost intractable.
Ask actually something on the slide, Jason.
Yeah.
Like, I'm trying to interpret the F star and G star formulas, and they're kind of tempting to interpret.
Yeah.
Just kind of look at G star. It looks like you're just taking some ensemble. I just mean like a linear combination of like the mu you would have gotten if you just like had thought only about like if you just had forgotten basically about the side information, and this kind of richer eta that you could have tried to extract from your side information, right?
Yeah.
So like, is there a relationship between what you're doing and ensembling over some collection of models?
Yeah, probably there is a story like that. So for example, if I had different sources of side information, then probably actually this would become kind of an ensemble or a convex combination of different projections onto spaces of variables corresponding to all those sources of side information. So in this case, we just have one source of side information, right? Just one W. But if you had many of them, probably it would be some kind of an ensemble, and so you could maybe even think of it that way.
But you could also just say maybe I'm ensembling like from F star or like from mu and eta.
You could also think of it that way. It's just a two-component ensemble. Yeah, you could think of it that way. Yeah, I see what you're getting at. Yeah, that's right. Yeah, that's right. That's right. Yeah. Any other questions? Yeah. So another question that you might ask is, okay, so when can we expect this correlation to be small, and is there sort of an interpretable way of thinking about when it actually will be small? So you can use the Cauchy-Schwarz inequality on this correlation, as well as the law of total variance, and you can completely remove actually the dependence at least in this upper bound on the deployment model, so on the F hat and F star, and so you can upper bound the correlation in terms of the variance of this conditional expectation of the of the rich view error given X divided by the sum of these variances. So this variance here is the total variance, and this variance here again is the variance of the conditional expectation where I'm conditioning on X. And you can also show, just by conditioning, that this variance of this conditional expectation is equal to the variance of the conditional expectation of my rich view model given x minus mu. Okay, so what this suggests is that there's some kind of like smoothing effect going on here by smoothing out w given x, right? Because this is the expectation of the conditional distribution now of z given x, so of x and w given x, and so I'm smoothing out w here. Okay, and so we kind of know that whenever we're conditioning on things, right, we tend to decrease variance. And so another way of saying, okay, well, when are these errors going to decorrelate? When is this correlation going to be small? Can also be said as saying that this variance of this kind of conditional expectation, we're conditioning on w and conditioning on x and smoothing out w, is sort of small relative to the total variance. And so again, this is another way of saying that this correlation is going to be small if w provides information about y that x doesn't capture. And actually what's interesting is that this smoothing effect here was actually first noted by Eric and Martin in their paper. Of course, they didn't talk about correlations or anything of this sort. So if you look at their risk bound, so their risk bound actually contains an additive term, which is the absolute error of this sort of smoothed out prediction that you're having from their rich view model minus mu. And so they say, okay, well, if this is small and if this is under control, then your risk bound is going to be small. Whereas ours says that you really only need to have the variance as being small, kind of in a relative sense. Okay, so it's not an absolute sense; it's more of a relative sense. And so what ours is really saying is that the error here actually doesn't have to be that small for you to still get benefit from doing from incorporating this side information. It really just has to have this relative scaling that's small. Okay, so it's a much weaker requirement. Basically, just have to have a relative control on the error, not an absolute control. Okay, so another thing that I want to do is just to talk about a high dimensional extension. So we were kind of playing around with these things in high dimensional spaces. So when the ambient dimension in X and W are extremely large, and we were encountering some issues with optimizing or minimizing this L hat criterion. And so one of the things that we thought was, okay, well, are there some algorithms that we can use to make this more tractable? And so one of the things that we landed on was using a dictionary-based approach, so based on greedy learning. And so in other words, we kind of build up these models incrementally. And actually, if you kind of think about it, if you go back to the way that I introduced our algorithm, right, it's kind of this back and forth method. And so that kind of suggests that maybe you can use some kind of a greedy method where when you go back and forth between these two models, you're kind of building them up incrementally as you go back and forth, right? So as you update the deployment model and then recalibrate the pseudo-labels. And it turns out actually that's exactly kind of the structure that we exploit. So what we're going to do here is we're going to assume that my F's and my G's are basically just linear combinations of elements from some dictionary. Okay, and then I'm going to measure the capacity of each one of these functions using what's called the atomic norm. And basically, it's just the L1 norm of the coefficients in these expansions with respect to these dictionaries in these perspectives. Okay, so it turns out these quantities are actually going to control the approximation error for my method. Okay, so what you could do is you could think about this in a very naive way. You could just say, well, let's just do maybe what a statistician would do if they were approaching this problem, that is just very vanilla, very standard forward selection, right? So let me just expand the span of my existing model space by adding on the dictionary element from the F space and the dictionary element from the G space in such a way that I most reduce the objective that I'm trying to minimize. In this case, it's this constrained squared error problem, because that's kind of what vanilla forward selection would do, right? And then once you've selected that, right, you would then fit F and G on that span, and you'd grow the span by one at a time. Okay, so the problem with this though is that you have to search over the joint dictionaries, right? So the problem is that actually the complexity of this algorithm scales multiplicatively in the dictionary size, right? So you have to do this joint optimization. by the way, everyone kind of knows when I say forward selection, everyone kind of knows what I mean. It's basically just the same thing that you're used to in statistics and linear modeling. It's just now I'm using it in the sense that now I'm treating kind of this as a single feature that I'm updating here. So in this case, I'm just updating this joint feature across this joint dictionary and just expanding the span one at a time. Okay, but the important thing is that in this case, this naive way of doing forward selection, it's multiplicative in the size of these dictionaries. And so, if each one of these is large, I gave you an example where one was 20 and one was 30, right? So the product is actually pretty large. This actually can become pretty cumbersome to actually optimize things. And so the next thing that we did was we said, okay, well, let's exploit this kind of alternating perspective, right, of doing this, where I create, given some pseudo-labels, I fit a deployment model and I recalibrate those pseudo-labels. So let's propose something called alternating forward selection, where we're first given some pseudo-labels, okay, and then let's select an element from the dictionary in F in such a way that I, most reduce my objective function I'm trying to minimize. In this case, it's the squared error. Okay, and then once I've selected that psi k, then I'm gonna just fit my F by minimizing over the span. Okay, and then given a current fit, I'm gonna select an atom from my dictionary that solves this for the recalibration stage. Okay, and so the nice thing about this is that the complexity now is additive. Okay, and so you can handle much larger spaces without this blow up, and this actually really does make a difference. Yeah,
I'm gonna ask,
go ahead.
Can you fill that n as well by subsampling at each step?
Probably you might be able to. Yeah, you might be able to. We didn't think that far ahead. For us, the worry was more these, right? Because if you're in a high dimensional setting, like these are usually much larger than n. And so you could kind of, but yeah, no, I take your point. You might want to do something. You could do something more sophisticated, and you could probably think about the effects of that, but on the theory. But we didn't do that. Yeah, for us, the main benefit here was just going from multiplicative to additive in the dictionary size. Yeah. Okay, so what can you prove using this algorithm? So what you can prove is that the empirical loss at the kth iterate of this alternating forward selection procedure is less than or equal to the empirical loss at the population minimizers plus some error that scales like log of the iteration divided by the iteration. And then you have this kind of atomic norm here, which reflects kind of this capacity. And if you want, you can actually take this result. So this actually gives you a statement about controlling the optimization error now of the method. And if you wanted to, you could actually go back now to our theory, and you could actually just stick this directly in. We have a generalization of this that accounts for optimization errors. So you could actually just stick this in here, and then you could optimize over k if you wanted to, and you could get something. But just for the sake of brevity, I'm not doing that. Okay, so you get this log k over k scaling. And I think what was interesting to us is that you could compare this with what you would get if you actually did the standard forward selection, and you could ask, okay, well, how much do you lose by doing this alternating scheme? And actually, it turns out you just lose a log factor. So if you look at this classic work of Devore, so I guess your former colleague, the optimal rate actually for standard forward selection methods is like a 1 over k scaling. And so this alternating method, you basically you lose a log k factor, but the cost now is greatly reduced, right, in terms of implementing it. So we thought that was kind of interesting, and we had to use a lot of like kind of new tricks for analyzing these sort of alternating procedures with these greedy selection models that wasn't really available in the literature. So when we were first doing this, we were getting things like k to, I don't know, some like 1 over pi, something really bizarre. I'm making that up, but it was something really weird, and we were just not happy with. We're like, yeah, it shouldn't scale like this. And so then, yeah, we finally were able to show that it's a log k over k, and yeah, we had to do these kind of weird inductive arguments. But yeah, we were able to get this. We were quite happy with this. That you really don't get that much of a difference in terms of the quality. Okay, so just what I want to do briefly next is talk about how to extend this to other settings. Okay, so we considered a setting where you have the X, Ws, and Ys, so the paired data, and then you have this unlabeled data where you have just X and Ws that doesn't contain the Ys. But you could also imagine a setting where you just have X only as well, right? So you have X, W, Y data, you have XW data, and then you have only X data. Okay, and you can imagine that this could come up in many different settings, right? So I started off by talking about these medical settings where, you know, some patients have full lab tests, but even among those full lab tests, right, you can have different gradients in terms of the amount of information that they provide, right? So some might contain a lot more information than others. Okay, or for example, you might have a multimodal data setting. Maybe you have data that contains text and images, as well as data that only contains maybe text. Okay, and so what you can do is you can extend this kind of joint optimization framework to consider these cases kind of in a very natural way, right? So now what we're going to do is we can create two auxiliary models. So one is the rich view model that contains both the X and W data, and we can use that to do some pseudo-labeling. And we can do the same thing also for the unpaired data. It's just now the unpaired data is only going to have the X information, right? And we can fold this all into this joint optimization problem now, where we're minimizing over F, G, and H all simultaneously. And if you wanted to, you could also define kind of an alternating procedure where, you know, you update F, G, and H kind of all in a big loop if you wanted to. And importantly, now we actually have two constraints because we want to control the calibration for both of these auxiliary models to the true labels. Okay, so now we have two constraints. Okay, so just briefly going over some of the theories. So now actually you can define two decorrelation scores, and it turns out that these two decorrelation scores determine the quality of whether this additional data helps. So again, this is just the you know, how related the errors are between these two auxiliary models with the deployment model. Okay, and it turns out that you get very much the same stories. You kind of get this, you can bound the risk by the difference between the population loss at the empirical optimizers and the population optimizers, and you have this kind of 1 over gamma factor, and this gamma factor involves now both of these correlations. Okay, and if you want to, you can use empirical process theory to upper bound this. It's just that the upper bound becomes a little bit more nasty, and it's not terribly enlightening to see it. But again, you get very much the same story that if both of these correlations are strictly less than 1, then you can almost treat this as if you're working with the total number of samples being actually labeled, and in this case, it's going to be n plus m. I have n plus m, capital N plus m data points in total.
Can I
Yeah,
ask,
of course.
like, why is there no correlation between the two different models that appears? Why is it only the correlate like between the G's and the H's? Yeah,
it's a good question. When you do the math, it just that term doesn't pop up. Yeah. So you have to so when you prove this, you have to kind of expand these things, and you exploit very special properties about the F star, the G star, and the H star. And when you do that expansion, there's kind of not these cross terms in terms of G and H. They just don't appear. I don't know how to tell you other than it doesn't appear in the math, I guess. Yeah. It just doesn't come up in the math. Yeah. Yeah.
What is the interpretation of correlation back in G? You say the G was the one using W. But here H is only using X.
It is, yeah.
That is, I guess, some hybrid.
Yeah. Yeah. So again, you should just think of these as I'm using both of these models for doing pseudo labeling. It's just now they're kind of coupled right through this joint optimization problem. So even though H itself is only a function of X, it is of course, you know, it involves, you know, X data, W data, and Y data as a function of the data, because again it's tied up in this joint optimization. Yeah. So the interpretation here is just that I have these two auxiliary models that are used for pseudo labeling, and those pseudo labels help, and you can almost treat them as if they're effectively true samples, real samples, if these decorrelations with the deployment model, or if these correlations with the deployment model are not too big. So that's the interpretation. Yeah, okay, so that's the main message of this talk, is that side information helps when these rich view models that incorporate the side information and the deployment model aren't related, or their errors at least aren't related. And the way that we capture this is through this correlation, and it just comes up through the analysis. And the main takeaway is that the more independent these errors are, then the better the quality of the site information, and therefore the better risk bounds that you can prove. So I think there's a lot of really interesting future questions here. So the first one is, how do you adaptively select lambda or nu, and in such a way where you can maybe also prove things about the performance? I think, Boris, maybe one of your questions is maybe kind of related to this. Like, what if we have multiple sources of site information, right? So it doesn't just come from one source. So you have many W's maybe from different populations. And the question is kind of how do you integrate that together? And you can imagine that in many cases you will have data that comes from different sources. Another thing that I'm particularly really interested in is the setting where you have logistic regression, and actually you get some really nice math and some interpretations in this setting. This is kind of ongoing work. So in this setting, you can actually do very much the same thing. You can kind of think about these joint optimizations or these alternating procedures. It's just now the correlation isn't the quantity that actually measures whether these pseudo-labels will help. In this setting, actually, it's an information theoretic quantity, and not surprisingly, it's something to do with, it's like the mutual information, actually. And so it turns out that if this mutual information is small or large, then you kind of see this benefit or not. Another interesting thing that someone actually was asking me the other day, they're saying, okay, so if you're saying that the correlation between these two models is the thing that matters, why don't you actually build that in as a constraint in the problem? Right, so one of the other things that I could do, let's just go back to my original program here. Yeah, so one of the things that I could do here is I could add on a constraint, which is the covariance between y minus f and y minus g, right? It's kind of the correlation between those two. I could just add that as a constraint, and I could just use I could use just the empirical covariance, right, to do that. So I could actually plug this in. The problem is that actually now this problem becomes biconvex. So it's not jointly convex, even if f and g are convex spaces, and so the math becomes a lot more complicated in that setting. But actually, it turns out if you do add this constraint, actually things actually do become a little bit better. If you add this covariance constraint between y minus f and y minus g, things actually do improve a lot better. I don't know how to kind of incorporate that into the analysis because it's now a biconvex, not jointly convex problem. So it's much harder to analyze. And I can't even tell you what the population minimizers look like. It's kind of hard to characterize. Okay, so I think with that, I'll stop and I'll say, yeah, thanks a lot for the questions and happy to take more if there are any.